Okay, so let me pick up from the last time. The last time in the class number 28, we look into the equation of motion. We talk about the time discretizations, and from that time discretizations, we chop down the time, which is actually continuous, into the step, which is discrete. And as we have the discrete kind of time, well, then that make it possible to solve by numerical approach, because previously over the time window you have infinite number of steps, and now we just decide to just how to say, to be serious at given step. So we chop it down. The time stepping size is controlled, and we try to limit it to be small, such that the assumption, some of our assumption we use to construct this approach, which is the constant acceleration approach, we just say that the acceleration within a time step is going to be just a constant number, and as it is constant, then we tie up many things with just one unknown variable, which is delta u. So acceleration can be expressed in terms of delta u. Velocity, well, by the way, let me emphasize, we have the previous step information that needs to be known, and the previous step information is given by the superscript I. So the acceleration at the step that we want to solve, the step that we want to go to, is denoted by the superscript I plus 1. So the I plus 1 information, like acceleration and velocity, and likewise also the displacement in the next step, okay, is to be expressed in terms of the information in the I step, acceleration, velocity, and the delta u is for the step, the current step. It is the change from the I step to the I plus 1 step. So this is the only variables that we have for now. So life is much easier. Previously you used to have, oh, I think I should just change my delta u. Previously we used to have the let me change the color a little bit. Previously we had 1, 2, and 3 unknowns, 3 sets of unknowns. So total unknowns is going to be 3 times number of degree of freedom, total number of degree of freedom, which is like a lot. And the equations that we can cast from the equation of motion is going to be the same as the number of degree of freedom, because we construct the equilibrium at a given degree of freedom. So if you have n degree of freedom, that's the number of equilibrium you have, but the unknowns turns out to be 3 unknowns. If you do the time discretization like this, you have 3 unknowns, and 3n unknowns is like 3 times as much of the equation you have, of course, because actually all these 3 are ties up, right? In reality, the u dot and u double dot are ties up together. So it is just the derivative of another, just that. But we do not want to solve the differential equation in the big series like this. And you have no idea still that the differential equation that you are dealing with is it like a monster to you or not? Well, if you are looking up looking at just the simple, very simple kind of function of u with time, of course it is possible, and that's gonna push you out. For example, if you have the function of u given in terms of the sinusoidal function of time, that is going to be simple, and you can just change all of this into the frequency domain analysis very easily. But we are not interested in such. Just the frequency domain analysis, everything is a sine function. Well, it is still useful in many applications. It is still useful for some sort of measurement techniques like ambient vibration measurements. Okay, all of that can be still useful. The very simple frequency domain analysis could be good in that aspect. But we are aiming for many something that is much more challenging than just that frequency for just the simple sinusoidal function of u. So what we are looking at now, we need to deal with the transient sort of functions of u, and then it is not that easy to solve. And you can imagine how many unknowns you have. Right now you have n degree of freedom, so you have n unknown displacement u, and displacement u, each of them are not having the same function, not the same function of time. So that's a lot of headache you might encounter. Thus, when we change from the closed form, from the effort to try to solve for the closed form solution of u, that will be like a bunch, and that will be messy. We just say that, okay, u is one thing, the velocity u dot is another thing, and u double dot is also another thing. That breaks down the unknown that used to be 1n, but that 1n is a crazy function, okay, n numbers of crazy functions of time, into 3n of independent point values. So u is associated to the step u dot, and u double dot are also associated with a given step. So we broke down this way. That means the consequence is the multiplications of the unknowns from 1n to 3n, and that's why we spend time trying to come back to the n number of unknowns again, because you do not want to find 2 times n more equations to solve. It is not possible. If it could be done, people must have done that already. So in order to do that, the most important assumption there is that the accelerations from the step I to step I plus 1 must be constant. So if we have the constant acceleration, we can use the formulas from the high school physics for those equation of motions you learn in the physics course, that S equals to ut plus a half at square, and v equals to u plus at, so on and so forth. All 4 formulas like that can be used over here, and all those formulas are derived from the given constant a values, okay, or the acceleration is constant. So we adopt that concept. And first of all, the easiest thing is that the u at the step I plus 1 has to be the u at the current step, okay, plus the delta u. So this is the displacement increment. It is quite straightforward that the next step must be this step plus the increment. So this is simple. And then we use the s equals to ut plus a half of at squared, which is this thing. We have just a different form of the unknowns or the variables, which is the u dot, etc. Alright, we crunch down things, and then we go through and we come up with the expression of acceleration at the time step I plus 1 being the delta u, okay, as the desired unknown. We do not want other unknowns but delta u. And then you have the information at the step I, which is the previous step, and it is the known value, so you are happy with it. This also a known value, so u double dot at step I is another known value. Now I think maybe the question arises. The question could be, well, sir, if I am at the step 1, the first step, what would it be? What would the u I and u double dot I? Okay, you want to start the analysis. You are at the step 1. Well, it's up to you. Time 0. Let me say it that way. At the time 0. So you might ask, okay, if the time 0 step, how do you know the previous step? In general, the analysis is going to be carried out in a way that we assume that the previous steps everything is 0. The structure is at rest condition. All right. So the u double dot I, u dot I, everything is gonna be the 0, and basically you're gonna ramp up the response of the structure, not the response, the excitation to the structure after a short period of time. So over here everything could be 0, u equals 0, u dot equals 0, and u double dot equals 0. So the initial condition you give over here is not going to give like a very sudden or give the hard time for the convergence, or hard time for the solution calculation for the in the equilibrium. Okay, so everything starts from 0, and then you just ramp up your excitations, and you're gonna get the nice simulations then in the dynamics point of view. Sometimes if you just put some condition that the displacement is going to be starting just very suddenly, okay, the acceleration could be really high, and you're gonna get some sort of like the peak jump in everything. Okay, then we have seen the u double dot I plus 1, and also the u dot I plus 1 is coming from the same concept. So it is just the u dot, and everything is given in the I step, delta u, and I step. Other parameter like beta, gamma, delta t are all known. So we will just come to here. We use all the terms. We have the equation of motion is cast at the step I plus 1. So for the step I plus 1, the u double dot will be taken from before u dot is also taken from the previous page and just the u also. Alright, so we expand, so u double dot I plus 1 is expanded into here, here to here, and this to here, and we rearrange. How do we rearrange? We rearrange terms such that the delta u, okay, stay together, and the other green terms are staying together on the different side of the equation. So if you have just the dynamic problem, if the system is linear, okay, if your calculation has nothing to do with inelasticity or nonlinearity, you end up with this, and you are good to go from here. So what you will do is just to determine the delta u from the one step to the step I plus 1. And the right hand side terms, they are about the how to say, the right hand side terms are all known. So everything is known, and if everything is known, what you end up with turns out to be just a vector. So this is a vector of force at the step I plus 1. This is a vector of force as well, k times u, okay, and other things, c times the terms here and there. Okay, so right hand side adds up to be just one vector, one-dimensional array, whereas this left-hand side is the matrix. So this matrix contains what? Whatever that is multiplied by the delta u. First of all, the k. So the stiffness k. This describes the structure. And if we are talking about the linear problem, then the k will not change. C. Well, if it is just the dash part or something with the constant damping, so C wouldn't supposed to change, but if C is changing, then you might end up with the nonlinear problem. And mass matrix is generally not changed, right? So mass is always there, and the mass is coming from the calculation of the contribution of mass to a given node. Okay, so the effective stiffness matrix is on this left hand side. We call this one effective stiffness matrix. If nothing is changed, then you just recycle this K effective, and many cases you can just play with the elastic problem, linear problem, and you can run the analysis this way. It will not take you much time. It is going to be very fast when you run the linear analysis, and if your code can be, you can control your code and it reuse this number. It doesn't recalculate the stiffness every time. Well, the recalculation of stiffness is not bad, but the part that you inverse the matrix is a bad one. And that is also applicable to the cases that for a finite element we do not really inverse the matrix. The reason is that the inversion is expensive, and I used to talk about a solver that save your cost. It is the sparse solver and super LU solver. All these things are going to, the operation of this solver are going to be pretty much like it's going to be resource consuming. Let me put it that way. It is not pretty much like the inversion, but it is resource consuming. So you do not want to mess with this part for many times. If it is linear and if it is elastic, just go ahead, reuse this, and you're gonna end up with a fast calculation. And over on the right hand side, you will just keep changing things. Okay, we'll see. On the right hand side, you change a step, all the green parameters are going to be always changed, right? You move to the next step. Now you fix everything and you solve for the I+1 step. The I+1 step, once it is solved, it will turn out to be the I step. It will be changed in our sense to the I step, right? Because the I+1 step, let's call it the number. If it is the step number 10, I+1 is equal to 10. Once you finish the operation, then the 10th step turns out to be the known step. So 10 will be the I, and the 11 will be the I+1. And then you solve for the 11, and then the 11 turns out to be the I, and the 12 turns out to be the I+1. So things is going to roll over like this. I am terribly sorry about the poor quality of the internet connection. That frustrates me real bad as well. I try to make the teaching smooth such that when it is on the YouTube, the internet problem is not going to bother you for another time. So really sorry about this poor internet problem today. It has been disconnected for several times, and I was trying to click and reconnect everything back and try to push it back to normal quite several times, 3 to 4 times already. I know that you get frustrated real bad about this, and this is going to be available on YouTube, so please be patient with it during this hard time. I don't know how to resolve the issue. I might need my personal internet connection, which is like independent from my home, to avoid this issue. And this issue always occur every time I teach. When I'm not teaching, then there's no such problem. It's quite interesting why. Well, anyhow, what we evaluate everything. The thing that is that keeps changing. Another thing is the f at the I+1 step. So the forcing function in the dynamic problem is always changed. So we have these two here. If we are happy with linear analysis, just use this one, right? Your life will not be so messy. But if we opt for something more complicated, if the issue is about nonlinearities, the next page is coming in. So I call these two parts, we have the K effective, and the right hand side I call it the RHS. And this RHS is a function of other things. It is a function of what would it be? The U dot U dot I and U double dot I. So it is just a function of previous step information. But one interesting okay, the I+1 is in there, right? So the I+1 step information is also inside the right hand side, but it is simply not a function of U, of course. And the knowledge we had in Newton-Raphson nonlinear strategies, that we first of all we write the equations, the nonlinear equations, in terms of the residual. So we know that the equation we are talking about here is nonlinear, and we try to solve this nonlinear equation by introducing the residual terms being k effective minus the right hand side, just like that. So this residual was supposed to be 0 because it is the residual of the equilibrium. This is your equilibrium equation, dynamic equilibrium from the equation of motion. So if the equilibrium is there and k effective, this side is equal to RHS, then once you move it to the same side, you're gonna get the 0. So residual has to be 0, supposed to be 0, and we can approximate the residual by the R evaluated at the delta U naught times the increment of delta U, and this part is the tangent. Or I think I can recall your memory, which might not be here anymore with you. So if you think of this picture, if you realize what this thing is, that means you're still having some knowledge from the computer method class, and we try to solve the nonlinear function like this. And okay, this is the target, the force that you apply. So in order to do that, I will this point is going to be our delta U naught. This is the point where we it is the current point. Let me put it this way. So if you recall, we have the unknown. This is the given force. You apply force in the last semester. You apply force, and then we get the corresponding displacement. But once you evaluate the internal force that provides the resistance to the applied force, you know that you still have this gap. So this turns out to be the new current point, and then you make the projection from this current point. So this is the difference of the force that you have currently to the target force. You get the increment of the displacement to here, this new point. You re-evaluate the force turns out to be still lower than the target force, so you project again. So it just works like this repeatedly, and this is a concept we had for the Newton-Raphson. So the R evaluated at delta U naught is this one. So your delta U naught is moving along. Once you solve, you get the value of the delta U. Okay, you update and you evaluate the internal force resistance from this new number, and you start calculate this from the current point, the residual from this point, add up with this is the delta U minus delta U naught, right? And this is the K effective. So we calculate this part here. You know K effective, you don't know delta U minus delta U naught, but you know the R evaluated at delta U naught. Okay, so you get this one from your calculation. Once you get the delta U minus delta U naught, you update. You come to this point, and then it is possible for you to evaluate the residual. And your residual, now the delta U naught turns out to be this number. So you update the delta U naught. And you keep going like this. And the detail about all of this is actually given in the computer method course already. But the only difference is that previously we just talked about the static equilibrium equation. Now we are talking about dynamic equilibrium equation, but you just set aside the word dynamics. You just set aside the part that is scary, and then you just look at the variables, and then you treat it just correctly mathematically, and you're gonna end up with a nice should I delete? Okay, I can keep it that way. I do not need to delete it. And ultimately this one works. So this equation is going to work, and it is the backbone for the nonlinear dynamic analysis. You solve this equation. So R at delta U naught, evaluated at delta U naught, which is the point that you just get from step before, right? What is inside that R is a K effective delta U and minus right hand side. So at the very first step, the delta U has to be 0, right? And well, we're gonna see how things work and in detail of each variables. And here this is the Taylor expansion. So this part here evaluate first, and then the delta U minus delta U naught is this part here, which is to be determined, and then the partial, the tangent of the function of R with respect to delta U, which is the slope here, and it turns out to be the K effective. Maybe I should, yeah, I think I make this video self-contained then. So I will not expect you to go back and read any information we had from the previous semester. Well, it will be better, yeah. Okay, yeah, make it nice and big and clear, and hopefully it's gonna be useful then. So this vertical axis denotes the I keep it just at delta U, and this is the delta U. And you have the function, nonlinear function, like this, and you have some sort of target. Okay, so for the first step, let's okay, it goes like this. you use the initial tangent from okay, you get the solutions, and this turns out to be delta U, we should call it delta U1. And when I say that, so first R was evaluated over here, right? The delta U0 in the meaning we had over there means the current point. Just understand it this way. So R delta U0, okay, is the current point value, and the current point value of R delta U0 here is equal to 0. Okay, so you get the K effective from this slope here, and you solve, you need to get delta U minus delta U naught, and it turns out that the value is equal to delta U1. Okay, then the procedure just proceed this way. So the evaluation of residual is changed to this next point, delta U1 is coming in, which is this thing. So the number one U1 is coming into this delta U0, in the meaning that the delta U0 is the point where you are, and we found that it is non-zero, and you have the difference between the red line and the current point. So no. Could it be better? Okay. The difference is evaluated from this point here. Now you get the new solution. You have the let me move this. Okay, you have the new solution, and part here is delta U2. Let me put the 2 down. Okay, 1 and 2, 1, 1. Okay, 1. This is 2 minus delta U1. Okay, just like this. You re-evaluate the values over here. So the sense of different one. The sense of delta U0 is coming to the point that I just moved to. Okay, so it will be moving along like this. Now the equation here is going to be used. So let's take a look a little bit in this, which is the nested loop we have. We are talking about the domain of time, and we discretize the time into step. And in each time step, you are going to have the nonlinearities. Okay, we are trying to solve nonlinear problem within the step. The thing is that the step shouldn't be too big. When the step is very large, then the convergence from the nonlinear problem is going to be the issue. It might be more difficult for the code to get the convergence, and you do not want to have too many iterations in order to converge. So first, on the left side in the brown text, in the brown writing, brown color writing, that denotes what's going on in time. But the purple color here just denotes your nonlinear iteration. Nonlinear iterative solution. Okay. So the iterative solution is going on within the time step, and you start over here. What you have is that the information from the I step. So the residual will be computed from the I step. Now I am going to expand the residual terms, which was from the previous lecture. Okay, I put it here already. Let me put all of them in place, and let me try to talk about each of them individually. So we have the mass term, the damping term, the K term, and the applied force term. This is coming from the right hand side. And the left hand side term is here. Okay. But all of these are going to combine into the residual. Basically, this term here, to be precise, when we talk about nonlinear problem, it is not the K times U. It should be represented by the P internal. It is internal force. It is not evaluated by K times U, because the constitutive model of your material, of your structure, will look like this. So if it is the U and this is the force, it is not just the K times U, right? Your U is here, but force is here, but K times U. What K? What K? The question is what K. So it's actually the function of P, which is well, the UI, like that. So this is represented correctly by the P internal. The K will be substitute, and not substitute, will be the K tangent stiffness, which is evaluated from the current U values. Okay, so residual come from this. I need to put in the sign. So if you see on this one here, if I have the K effective delta U minus right hand side, So this is the K effective times the delta U, and then I have to minus right hand side. So I'm minus and I'm minus. Okay. Well, ultimately we end up with the evaluated at delta U, and it was supposed to be delta U naught. Right. Okay. So this part here is from this I plus 1 step. Other things from the I step, okay, or other information from I step. But the thing that could be changing is in here. So your R delta U naught is going to be starting from here and then moving to there. So as it moves to there, then delta U naught is going to be updated from this number to this number. Alright? And then you're going to move to there and there and there and there. So this depends on how easily the convergence is obtained. If the convergence is simple to obtain, if you don't put the program under the difficult time for too much, you're gonna need quite just a few, 2 or 3 iterations, and then you get the nice convergence. If you have 5, 6 iterations, that shows clearly that it is encountering the problem in the convergence. We will probably we will get a chance to write the code for this problem. Previous semesters I just stopped at the equation here, so that is for the linear problem. But if some of you need to make the nonlinear code and for the time history analysis, this is going to be the good opportunity. And again, lifelong learning, so you do not need to stop watching this video just at this point here. You can just keep watching the update that will come later and later and later, and the part that we write the code is going to be very time consuming, so it can be, we could add it in. Okay, will it take care of negative stiffness after ultimate? That's a question from Silvaram. It mean what? It depends. The scheme that we are dealing with right now is the Newton-Raphson scheme. Newton-Raphson or modified Newton-Raphson is going to be in trouble when the material is having the zero stiffness. So when it is approaching to the peak, the flat part, it's gonna be in trouble. So the convergence is not going to be possible. There's gonna be some techniques that will be used along with in order to stabilize the calculation. But we do not go to that point for this course. But there will be the schemes to use to fix the given problem after the, well, that, as you said, after the ultimate. Many times the calculation or analysis still continue even though some of the material are approaching to the ultimate state. So some part of the beam might be crushing. It reached to the crushing strain. Concrete there might be going flat, or steel might be yielding. But if the other part are still intact and carried over the load from one place to another place, then the analysis might still continue. So that depends from problem to problem. As long as the overall structure, the stiffness of the overall system is still okay, then the analysis still continue until you get to the real ultimate point of the structure. It is not the local point, it is the structure ultimate point, and that's gonna stop without, if you don't augment the code with the technique that stabilize this issue. Okay, but as much as we talk about from these two courses, we are capable of going all the way to the peak, to the zero stiffness part. All right. Okay, so that is pretty much for the implicit time integration approach, and we have another techniques and another scheme that is friendly for the different scenarios. So this approach is good. Well, it is very stable, it is robust, but the point is that you can see what's inside your calculation. That's a lot of things that's going to take a lot of your computer resource. Well, the time stepping size could be bigger than the explicit time integration due to the stability of the scheme. The implicit time integration allows you to use the bigger step size. Both implicit and explicit time integration is going to handle nonlinearities fine, but due to the natures of the nonlinear problem, we want to discretize everything into the smallest size as possible. So in the spacious domain, we discretize the x, y, and z, the domain, the physical domain, into the small size in order to pick up the nonlinearities properly. Otherwise, if you use the large discretizations, you will not sense the nonlinearities at the same moment as the finely discretized domain. Because nature of finite elements, as you know, if everything is discretized, if the domain is discretized, then the displacement within the domain is going to be approximate or interpolate, and the interpolation functions that we have are not capable of picking up the point or the localized information about the nonlinearities. When nonlinearities occur, it starts from like a small point and then it spreads off. So if the mesh size is big, that means the sensitivity to the nonlinearity is going to be lower. You pick it later. Sometimes you don't even pick up the nonlinearity, whereas the better model picks up. And that depends. That is the skill of the user of finite element program. At least you need to understand the nature of FEM before you use it. Okay, but that is in the domain, in the physical domain point of view, that the discretization should be done in a very small size manner for the picking up of nonlinearities. And then you have seen some explanation that some elements which is very cheap, the formulation is very cheap. You don't get the nice variation of strain in that element, but the discretization is very rigorous. That's the fine mesh problem along with the cheap element still gives you the very, very satisfactory solution in comparison with the very nice element, very novel element that use the better shape function, better interpolation functions than just the constant strain like that. But due to the cost of the calculation of the expensive element, then that is not feasible to use for the small mesh, and then you end up with the trouble about the memory, the RAM that will be used for the calculations. And it turns out that you can go with the cheaper element with the better discretization, and you might end up with a better result and faster calculation. Likewise, not only just the spacious domain, we are talking about time domain now. And in the time domain, the implicit time integration is like the Q elements, very nice, novel scheme, very useful. When the time stepping size is allowed to be bigger, when you are dealing with the problem where the nonlinearity is not so crucial, it might be your choice. It might be good for the time that you do not have the nonlinearity. So when you run the transient analysis, you run go and go and go. Maybe the time window that does not trigger your nonlinearities could be long. You might just use the implicit time integration for the given period of time until you bump up into the issue like the nonlinearities. At that moment, you can rematch. First of all, you can rematch your structure. But again, if you use the coarse mesh at the beginning, at the very beginning, you will hardly detect the nonlinearity. So it is the irony that you might not be able to simplify the problem by just using the coarse mesh at the very beginning. But something like you can look at the excitation, the forcing function, or the input force. If the magnitude is not high, that means okay, you might be eligible for using the bigger time stepping size and also bigger mesh size. And once you see that the input forcing function is questionable or suspicious, you expect that nonlinearity is going to be there, then you stop the analysis somewhere before and you rematch. And well, that's going to take a lot of effort of the programmer, but it might be the features which is available in the FEM software already. You just restart your calculations. The new mesh is going to absorb the information which is obtained from the previous part of the analysis. So you're going to have the sets of stress and strain in the given new elements, and you change from one scheme to another scheme. So you change from the of course the coarse mesh to the finer mesh. That's one thing. And another thing, you might change from the scheme that is the explicit time integration into the implicit time integration into the explicit time integration. You chop down the time stepping size into a much smaller one because the explicit time integration is prone to the stability issue, instability. So you can end up with the problem in the analysis. You can end up with the unstable calculation, and it stops. It gives you the bursting out of the solution. It blows up. Okay, so let's take a look into this explicit time integration. We can call it a central difference. Just emphasize a little bit. I talk, but I want to also write it down clearly here that the delta t has to be very small to ensure the stability of the analysis. Okay, once you use too big delta t, that's the end. And we are going to look at the issue in a little different way. Still, the time discretization is required. Okay, so this is a picture I draw in the previous class. And we have the time step I minus 2, I minus 1, I plus 1, just like this. So the time stepping size is going to be defined in the same way as before. We call it delta t. So the stepping size equal like this. Okay. Now the time stepping size has to be equal. You are not doing things in just one shot like before. Before we are working on this space, but now as we are going to use the central difference approach, what is going to happen? Let's see. We are going to work at the center of the step. So between the I, okay, we're gonna call the new name So over here, well, still the size over here is delta t. It's not changed. But at this point here, we are going to call this duration number 1, and this the duration number 2. I should use the and velocity at the center of the step number 1 is going to be given by u dot and number 1. Likewise, the u dot number 2. Okay, they are 1 delta t apart. So the point is now we are going to calculate the velocity at the step I, and this velocity is u dot I is going to be the displacement at the I plus 1 step minus the displacement at the I minus 1 step, and divide this by the total time, which is equals to, so we take the displacement here minus the displacement here at this point, divide by the time, which is 2 times the delta t. Two times delta t, and the u dot 1, which is the displacement at the mid point here, the u dot 1 is equal to ui minus ui minus 1. Am I right? And then divide by the delta t. So we talked about the ui minus ui minus 1 and delta t. So you get the velocity at the midpoint. It is the average sense. And in the meantime, the number 2 is going to be calculated in the same manner. So it is I plus 1 minus u at the step I over the duration delta t as well. Okay. Next, if you know the u dot 1 and u dot 2, it is possible to figure out the u double dot I. The u double dot I gonna come from the u dot 2. Acceleration come from the change of the velocity, and the velocity that you use are the velocity at the middle of the step. So we have the mid-step velocity, and then they'll divide by the delta t. Okay, so what is the difference between this, and it is going on within the time window delta t. What's next? We expand this term. So the u dot 2 is given by displacement at the I plus 1 minus ui minus u dot 1. U dot 1 is here. So ui and minus turns out to be plus ui minus 1. And this is divided by the delta t, and then it comes down here, so it has another delta t, right? So it is the delta t square. And that will be nothing more than just the ui plus 1 minus 2 ui and plus ui minus 1 over delta t square. Okay. Oh boy, I should delete this. So we move to the next page. We solve the equation. Okay, I put the equation of motion at the I step will be solved. So at the I step, then we're gonna have the m u double dot I plus c u dot I plus k u no dot I equals to f at the I step. Now, what is the beauty of this scheme? We're gonna see the beauty when we come back to this point here. Let me take something from here. Go to the next page. Okay. And we plug in. So start with the u double dot I. It is replaced by this plus c u dot I plus k u I. So the formulation is at the step I, but the parameters or the unknown that we determine is not the step I unknown. The step I informations are all known. Okay. Step I information are all known. The only unknown we have will be from the step I plus 1. So I change the color. And I change the color here as well. So you can see now everything is known but just the UI plus 1. So generally, if you do not have anything to do with C, or if you can express the C in terms of the M, okay, we're gonna end up with a very, very beautiful life. So let's rearrange these terms a little bit. The point is that in order to achieve the so-called beautiful life, your mass matrix has to be the lumped mass matrix. It is the condition. It has to be the lump mass matrix. Why? Because if you have the lump mass matrix, this is the thing that you end up with. Lump, what is the lump? The nature of lumping is to just pretty much like the tributary area basis. When you calculate the column load in steel, in a concrete design, you compute the tributary area of the column. It is the same concept. So you get the area which is associated with a given point, and then you lump the mass to that point. So we're gonna have mass 1, mass 2, mass 3. That is for a point. And then 0 elsewhere. So you have only just non-zero band Well, you have some coefficient, right? 1 over delta t square. Your mass matrix 1 over delta t square, and then it is multiplied by the displacement. Pretty much like this. Multiply. So this is u I plus 1 step, but at the node or degree of freedom 1 u I plus 1 at DOF 2, and so on. So this is what's going on here. This U is going to be changed into the red color, so you see the correlations with the above. So what's going on with the other things? At the step I or step I minus 1, they are all known, and since they are all known, they are equal to, first of all, you have the f I on the right hand side. You need to minus the k u I. This term might be replaced by internal force, because it might not be the linear problem at the step I. And what else? Other things are known. So minus m times the copy and paste. Okay, and it is like this. Okay, M, and the C, if you want, if you have the C matrix in there, it will appear. But again, the damping, when you run the analysis, the damping come from what? It comes from the nonlinearities of the you end up with hysteresis damping, right? So if you have the nonlinear problem, you treat the nonlinear, you treat the damping properly. The source of the damping comes from the nonlinearities. Okay. All right. Now, still in the big picture of this, why is it beautiful? Okay, you still wonder, I know, why is it beautiful? You look at these formulations. The right hand side are all known, so it is just one vector. All right, easy. The left hand side, due to the use of the lump mass matrix, that makes the diagonal to be just the non-zero, and the off-diagonal terms are all zero. So what kind of equation you have over here? You have uncoupled equation. Uncoupled equation. M1 multiplied by this one equals to the first row of the vector here. Am I right? M2 multiplied to this is equals to this. So you have just a lot of uncoupled equations. You do not need to inverse the matrix. Here is the beauty. No matrix inversion. The computer is just giving you a big smile, and it tells you that, okay, this is a piece of cake to me. So you just, not you, the computer will just find the ui plus 1 by taking the m1 and divide on the other side, and then you have just the delta t squared going to multiply on the other side, and that's it. As simple as that. Finish first equation, go to the next equation, go to the next equation, and next and next. But there is no matrix inversion. and the peace comes in. Life is beautiful. The only ugly thing is that due to the nature of simplifications of this scheme, you might experience the unstable condition. And the unstable condition generally comes from the time stepping size issue. So the time stepping size has to be extremely small to make this scheme possible to use. So good discretization in space and good discretization in time is generally the requirement in order to use the simplified scheme. Okay. What else? Let me check one thing I think I missed is the mass matrix. There are two kinds of mass matrix. I just talk about lumped mass matrix, which is for explicit time integration. The next one is the consistent mass matrix. And it is for the implicit time integration. There's a reason why it is called the consistent mass matrix. Yeah, people name it for a reason. Just like when they name the lump, that is really lump. So the lump one the concept of tributary area was used. So you have for the linear shape function, you can have something like this, and then you assign the area. So you take the area each area and then multiply by rho, which is the density, and then you assign to a point. So this one has the rho maybe A1, A2, A3, A4, row A1, row A2, row A3, row A4. The point is that right now we assign this number to the points. When we construct the mass matrix, we gonna construct it based on the degree of freedom, right? So we have if this is a 2D problem, then you have 2 degree of freedom at each node. So you have 4 nodes, you have 8 degree of freedom. You're gonna end up with a mass matrix that looks like the row A1. I'll omit the row because that's gonna be outside the matrix. A1, A1, A2, A2. It's gonna look like this: A3, A3, A4, A4, and diagonal line. But okay, so it forms the diagonal band like this. And the condition is that it is associated with the U1, V1, U2, V2, like this. Okay. How about a consistent mass matrix? It is consistent for a reason. Consistent means consistent to the consistent with the shape function approximation. Basically, energy calculation. If you think about the kinetic energy in the given elements, if you want to find the kinetic energy, right? It is the a half multiplied by the rho, which is the density, and you have the velocity square, and then you have the area, okay, which is the domain. It will be the volume, it will be the area, okay. This part here, your u dot square, your u dot is given by the function of the delta u, and this is approximated by the shape function. So you're gonna end up with for example, 2D problem. Okay. Oops, sorry. Where's it? page. Okay. So the mass matrix itself, if we pick up from this point, a half times the m, v square, and let's take a look at the displacement vector. We have the u, we have the v, and the kinetic energies. What should I use? So it goes from degree of freedom to degree of freedom, right? For the u direction of it, actually should be the x. xy repeating like this, and so on and so forth. So how does it look like in between? So the kinetic energies in the x at the first node, e superscript 1 subscript x, is going to come from just the u. Okay, so 1 second, this matrix here, we're gonna have the phi 1 0, phi 2 0, phi 3, like this. Okay, so this is the screening out of the v. So v is not coming in. And the next line, it has nothing to do with the u. So you can see this. Okay. Now you have one set of this. But the thing is that you're gonna have the square term, right? So I should probably just move this down. This is just the way we take the u and we take the v. like this, and we try to find the energy. Okay, so that will be the square. So wait, I'll call this matrix let's make it the R matrix. So you're gonna have the R transpose multiplied by R, okay, and multiplied by rho, and integrate over your domain in order to, sorry for the kinetic energy, it was supposed to be given out this way. It should be just the energy in the X and in the Y, yeah, just like that. And you have the integration in this domain multiplied by rho, and then yes, okay. And you have the displacement vector out there. We pull it out. Square up. A half should be out there. But that is not the essence of this activity. The main important idea is that here inside is the consistent mass matrix. So the mass matrix from this approach is not violating the mathematics and the physics when you calculate the energy, kinetics energy, using the information you have from the displacement. Actually, this was supposed to be the velocity. Oh. Okay. Using the using the velocity and the shape function. And the shape function is in there, push inside, the velocity is out there, and the velocity will be given by the delta U. Okay, fine. But everything is going to follow the concept of the shape function, so it does not violate in the same way as the lump mass that you just assign the mass to the points, and that is not consistent, but it is good since you can enjoy the benefit of this diagonal matrix and the uncoupled equations. Okay. All right. So I think we can wrap up around this point. Well, it will be very interesting to develop the code together through all of these. We can play and we can test the schemes together and see the problems, and yeah, that will be the good thing. It is not a part of the curriculum of this course. The course, as you know, that we have 45 hours, so we cannot just go that far, just sit together and test things, test the develop the codes, every single corner of the course, and test it together. But I think the online learning is going to enable us to just keep going, keep working, and keep learning. When you have free time, you can get back and take a look at this together with me. When I have free time, of course, yes, I will have more free time if the courses are broadcasting in the future. So I will use the free time for the improvement of these points that we cannot stuff into the regular class hours. So we gonna play with the programming and see what's coming out of the numerical analysis. Okay, what is the problem? What should be expect, and to be able to see something before you really see it in the work. I don't want you to see the problem, to encounter the problem at the first time when you work. So if we can have that experience beforehand, before you run the serious finite element analysis in your work, and that will be better, so you know how to handle the situation. Okay, all right. But this is the last class of the FEM in the 2020 January semester. So we do not have examination for this course, and we had just the homework problem, and the last homework problem was the plane problem. After the plane problem, I developed the plate bending problem, and I think I don't have the room for you to play or with the code, because the code is fully developed already, and I do not want you to be the programmer. I think it is worthwhile to be able to code, but the essence of this course is to get you to understand the idea of FEM. So I'm not asking you to code up the part of the plate bending problem, like to find the internal moment like that. You already know the concept, so I'm not dragging you through the coding part. It's gonna take a bunch of quite some effort, and it is the computer science effort that rather than the structural engineering effort. Ultimately, what I want is that up to this point here, you know all terminologies about finite element. You know how finite element works. You know from the very scratch part that we developed how the shape functions is coming up, what is the use of shape function. The approximation of the displacement is given by the shape functions, right? And we use all of these shape functions, and we come up with the stiffness matrix. We discretize the domain into small pieces. We have the degree of freedom. We try to establish the equation of equilibrium at each degree of freedom. We start from the static problem, and ultimately we come to this part here. We come across the dynamic problem, but we do not really code the dynamic, but it is not so far from here. It is just a matter of fact that you have K already. You just need to find the M, you need to find the C, and you're gonna have a lot more information for the bookkeeping. But aside from that, the concept is not new. There is nothing special, and it's not beyond your capacity. If you are very active in coding, you are very interested in all this algorithm and coding, then you can continue with yourself, or you can continue with me when I have time to continue. After this, we're gonna be busy with the grading, with the examination, with the academic senate, with the the thesis topic. So I'm gonna have to think of this thesis topic. Probably we're gonna I'm gonna try to get all of my colleagues to come up with the thesis topic somewhere around. This is the April month, so hopefully at the third week or fourth week of May, we're gonna get the topic listed out, and the topic will be open for you to select in June. So the first week of June, we probably get the topic. You'll be free for a while, and if you are free and I am free too, I will just drag you to the course, to what we might not cover because we ran out of time during the regular course time. Right? Let's make this one like let's accumulate the knowledge up into this YouTube. So it does not need to be just 30 lectures. It could be 60, it could be 90, it could be 100 of lectures of this given course. Well, and I'm not the best in the FEM, I'm not the best in the computer method, I'm not the best in many things. Right? There are people who might be doing all this better. So you can also look up for the other source of knowledge. And I'm trying to do the best that I can. The concept of my teaching is to eliminate the pain that I had when I was learning. So I feel like I don't understand things properly when I was learning this, learning that. Then I try to fix the pain, and I also look up for the new pain to fix in the when I fix all the pain I used to have. Yeah? Okay, so lifelong learning, we still gonna see some updates in all of this in the future. For FEM, you don't need to worry more. I think I cannot assign more homework, so we're gonna give we're gonna look up through your assignments and the super assignments, and that will be it. Okay, so I'm gonna see you around when we do the research, and hope you have a good time with the examination in other classes. And if you are still around AIT, I know that many of you are still around the campus and traveling at this moment, even though you finished the final examination, but traveling back to your country might not be as safe as staying in the dormitory here. The number of the cases, COVID cases in Thailand these days is lower and lower. I mean the new infected cases. So the number is as low as less than 20 new cases every day. So it is quite safe here. It is quite safe. It is much better than traveling back and you will be quarantined for a couple of weeks before you can go out and see people. So it is useless, and there's no point to waste the money for the air tickets at this moment, because you are going to start the thesis very soon. Once you finish the final examination, you think about the thesis. And I know that this is the difficult time, and this nobody wants it this way. It is more difficult to do thesis because the laboratory work could be more difficult, and also the way the chance that you get to see the advisor might be more difficult as well. For my lab, I have like a regular everyday, let's say the daily meeting, lab meeting. It is the Zoom meeting. It is not the face-to-face meeting. So something it is more difficult, something is not that difficult. But okay, so we cannot complain. Yeah. Anyway, but just be ready for the thesis, and due to the difficulties in many aspects, you will need the extra how to say discipline, extra. You need everything extra from the people in the previous generations to graduate within the desired time. Okay, so I've tried to push. The sooner we can come up with the thesis topic, the sooner you can start. And once you start, just run. Just don't relax. I think you cannot relax because COVID is not going to let you go out. You cannot go for a grand trip. You cannot go for etc. trips because it is too dangerous to go out. So you're going to be locked in AIT and you're going to be doing the research. The thing is that the part that cannot be controlled by yourself, you've got to be very careful about those factors, right? Well, whatever, if you have anything, just email, ask me if you need some consultations, you want a Zoom meeting for class or for the other things like something about the thesis, then I can arrange the session. Alright, so we still can keep in touch even without the regular class from Monday to Thursday like this. I might have some sort of pop-up free class, so it is free for you. I might talk about some facts, some issues in the thesis if I can think of anything. So it will be good for me such that I do not have to talk too many times. If I want to complain about the PowerPoint presentations, maybe I just make one session and I'm gonna be very picky about how you should make the PowerPoint presentation for your proposal defense, or how could you do the literature review systematically, things like this. I can arrange the session and it could be useful for all of you, not necessary to be my student, my advisee. You can use all of these techniques or tips because it is the first time for you to do the research, so you might need something that will help you do it faster and more effectively. Alright, I think it is enough for today, right? And next week we're not gonna see each other again. We're gonna see it for the different occasion, not for the finite element class, but of course the FEM I might add it later, but not in the next week. Okay, have a good day and see you all around. I might be stopping by the campus maybe in a few weeks because situation might be better and I'm terribly bored of staying home for like too long. Okay, see you. Bye bye.